Okay, hello everyone. This is Mikhail Golovnya, Senior Scientist at Salford Systems. And this is our third webinar in a series of installments where we talk about trees and tree-based approaches and all of the wonderful things that you can do with those things. So the topic of today's talk is tree ensembles, the power of post-processing. So that will be the primary focus of the entire development that we are going to have today. The course outline, as usual, there will be a mixture of slides and some live runs. So we'll start by introducing ourselves, a little bit about Salford Systems, now that you've heard, some of you have heard all these previous talks. Then I will do a reminder on stochastic gradient boosting and TreeNet, which is going to be the core part of all of the starting point of the development here. Then we'll proceed by introducing two different compression techniques, namely ISLE and rule learner, with the core underlying methodology used to accomplish the compression as a GPS. And we'll finish with a few examples that will highlight some of the uses that we've had, successful uses of the technologies in the past, and it's a vast kind of developing area at this point, so I'll try to highlight some of those. First, just a few words about Salford Systems. We're principally well known for three reasons. Our products, all of them are either tree-based or tree-inspired, like Mars. In fact, we have a complete separate set of training series on all of those individual products. Our claim to fame is that we combine the power of academia and the speed of release into the world of commercial use and also academic use. And we also have a whole number of different awards, entries in multiple data mining competitions since 2000 and onwards. We have a very powerful list of major customers. In fact, some of our customers don't even allow us to talk about them, but the list that's presented here is based on some of the power users that presented at Salford conferences in the past, and we also have presentations and papers from them. And we also have partners all over the world, including China and Japan, and that also covers some of the Asian language versions of the software that we have. This is just a list of some of the awards that we had, and some of these awards are won by us, others are won by our clients or people who use our software, and sometimes it could be a little bit embarrassing when you get outperformed by a student of yours or someone who got access to the same set of tools that you have. During the presentation, as we go into the live runs, I will use the latest recently released version of Salford Predictive Modeling, SPM 7.0. You can download it on the given links. You can also use it 10 days for free or up to 30 days if you unlock it for evaluation. And you can always request whatever configuration options that you need. Now, the reason I'm using SPM is that the model compression techniques are the core addition that become an integral part of 7.0. To the best of my knowledge, you cannot have access to that same level of flexibility and the level of development that we've currently incorporated in 7.0 anywhere else. Okay, that concludes this initial simple introduction, and let me proceed by reminding of what stochastic gradient boosting is all about and how it works and what can be done with that. The technology itself is a new approach to machine learning and function approximation developed by Jerome Friedman at Stanford University. And those of you who don't know, Jerry is also co-author of the original CART as well as Mars, Prim, Projection Pursuit, and a whole bunch of other techniques, including things like GPS and post-processing techniques that we will talk in a moment. Stochastic gradient boosting is also known as MART, multiple additive regression trees. It's also known as TreeNet, which is the registered name that we use for the part of TreeNet in the stochastic gradient boosting inside of SPM. The nice thing about TreeNet is it's good for classification problems, regression problems, Poisson regression, survival. There's a whole bunch of different applications that the TreeNet can be used for. And at the core of TreeNet is that it's built on small trees, and therefore it has all of the nice advantages like being fast and efficient, data-driven, handles outliers, invariant to monotone transformations of variables. It's completely self-contained and can handle a large number of different modeling applications out there. In particular, TreeNet is known to be resistant to overtraining, which is always the point of concern in any boosting approach. And as we have, you have seen from the list of that major data mining competitions that we won over the past decade, TreeNet can be remarkably accurate with very little effort. However, it all comes at a price. The resulting model may be very complex, and it is the topic of our discussion today, is what can be done about it. As far as the algorithm itself is concerned, the way it works, you begin with a very small tree as an initial model, and at this point I'm assuming that at least you have partial acquaintance with trees. At some later slides we'll revisit it at a more elaborate topic. So you begin with a very small tree. Suppose you have a regression problem where you want to predict a continuous response. A very small tree is a first take on trying to explain that response in a data-driven way. It could be as small as one split generating 2 terminal nodes, but typically it goes anywhere between 4 to 6 terminal nodes. By default, it uses 6 terminal nodes. And then the process continues in stages. So you have compute residuals, prediction errors for this simple model on every record in data. Then you use these residuals to grow a second tree that it tries to correct them, and you continue in that fashion until you build up the whole collection of trees, and you also keep an eye on performance on the independent test sample, or perhaps cross-validate to identify optimal configuration of those trees that will be used as the final model. So that's the core algorithm. We had a whole webinar dedicated to it previously, so if you're interested, you can always get those recordings and refresh and have a refresher course in that. What I'm going to emphasize here is a more detailed representation of what may happen inside of the TreeNet model development process. What I have here is a toy example that has 500 observations with only 2 variables, x1 and x2, randomly drawn from a -3 to +3 symmetric box. And I have constructed a so-called exclusive OR response, which is simply y equals as a product of those 2 variables. Now, in spite of the simplicity of this problem and the simplicity of analytic representation, the problem is known as a pretty difficult problem to handle by a large number of different data mining techniques out there, especially the ones that are designed to learn from the data. Now, the problem itself is very useful to show how, for instance, TreeNet will handle it. What I did here, I've constructed a sequence of TreeNet models from 1 tree to 200 trees. Each tree is only 3 terminal nodes. And the plots here, they're shown in x1, x2 space as heat maps, and the color coding corresponds to the predicted response at the corresponding area of x1 and x2. Now, as you can see, the very first tree attempts to essentially cut something along the x2 axis, and then on one side it also cuts along the x1 axis. That creates three separate regions, which is exactly the three-node tree we're looking for. And in each region there is a certain adjustment. The red adjustment points towards higher levels of response, the dark blue adjustment towards the lowest levels of the response. As that tree is taken, the second tree is now trying to build on top of the first one, so it analyzes the residuals, and then it introduces additional cut points, so something happens here, and then the resulting model predictions are readjusted so that you have the new heat map. Now, as trees are being added more and more and more, by the time you reach 100 trees and especially 200 trees, you have essentially recovered that exclusive OR surface that we were trying to do. It's a saddle function. It's the function that increases along the 45-degree line and decreases in the orthogonal dimensions. So you have some kind of a 3D saddle, and that's essentially a major cause of complication in terms of trying to recover that surface. Now, once you look at these heat maps, what you will find out is that the tree net develops all of those individual parts of the surface in little chunks by repeatedly reevaluating things over and over again and constructing trees that are largely overlap, and they all try to reinforce and discover the underlying sequence. Now, what can be said about it? By the way, on this next slide, on the right-hand side, you can see a 3D rendering of that surface that was discovered by the software in this case. So the solution evolves slowly and usually includes hundreds or even thousands of small trees. In today's presentation, I will work with default settings of only 200 trees. In real production, it's very likely that you may have thousands of trees, and all of the concepts that we are talking about will become even more relevant. The tree development process by itself is what we call myopic. Only the next best tree given the current set of conditions is added. In other words, suppose you have 50 trees, like on the previous slide, you have 40 trees here. In order to add the tree number 41, the tree net has taken all of the existing sequence for granted. Nothing is changed, nothing is modified. The next tree is trying to improve the situation the way it is seen right now. And that's why we call it a myopic tree evolution process. As the result of that, there will always be a high degree of similarity and overlap among the resulting trees. You saw it on the previous slide, and it will be also reinforced by essentially analyzing all those tree sequences later on. Very large tree sequences, on the other hand, may also make model scoring time quite time and resource intensive. Now, when people first introduced into TreeNet and they see the power of its use and all of that, sooner or later the point comes when they want to deploy TreeNet models or stochastic gradient boosting models in real life, and depending on how advanced and how elaborate your modeling stage was, at some point you'll face the problem of deploying hundreds or maybe thousands of trees in the scoring cycle, and that in and of itself could become a challenge. Not as big a challenge as, say, in trying to deploy random forest models, but that's the whole other topic for a different time and day. Therefore, as the overall conclusion from everything that I've just said, there's an ever-present need to simplify or reduce model complexity. Now, what I've just talked about is a very simple toy example to highlight things the way they evolve. I'm going to revisit on the next set of slides the data set, the real-life data set that I used in previous presentations to build TreeNet models, and now we will proceed with this data set to show what else can be done. Just in a few words, the data set supplied during 2006 DMC data mining competition has to deal with 8,000 iPod auctions. They were held at eBay from May 2005 to May 2006 in Germany. Auction items were grouped into 15 mutually exclusive categories based on size, type, color, things like that. And then the goal was try to predict whether the closing price of the auction will be above or below the category average. Now, the reason we needed categories is because different iPods, obviously, they will cost differently. Therefore, you need to stratify based on type, size, color, etc. And then you try to predict whether the closing price will be above or below. Here is the available fields that we have. Starting with the product category name, and then there's all sorts of trivial things like how long the auction lasted, the type, the amount of offered items, some kind of feedback, what was the starting price, what is the buy now price, whether it was available, whether it was not available. A very typical data mining, predictive modeling application that often arises in online sales and online marketing out there. Now, this is a good point to switch to the software and have a first live TreeNet run. What I have here is Salford Predictive Modeler SPM version 7.0, 64-bit, running on my laptop. So I proceed by opening the data set. In this case, it's called iPod eBay.csv for simplicity, even though we do have access to a host of all of the different file formats. As you can see, 8,000 records, 19 variables, a lot of character variables, categorical variables, things like that. So I go straight into model. I pick TreeNet as my first modeling engine. Sort variables in file order, just because I know that the last variable is my target, a binary response, which is whether the closing price was greater than the average. Therefore, the run itself is logistic binary, and the most of the remaining variables will be used as predictors. As we usually do, this is an 8,000 data set, so I'll partition it into roughly 50% of learned and 50% of test sample. The TreeNet itself, we will use 10% learn rate. We'll grow 200 trees for simplicity's sake. Each tree is limited to 6 nodes. And at this point, the optimal model will be selected based on cross-entropy criterion. It's also known as deviance or log likelihood, perhaps with some scaling factors, either a factor of 2 or 1/2, depending on how you look at it. Okay, with that in mind, I'm going to start the modeling process. As you can see, TreeNet builds very quickly. The end result is the model that shows optimal solution at 177 6-node trees, and the resulting cross-entropy criterion, as you can see on the test sample, is 0.585. Now, whenever you do modeling, you want to keep an eye on model performance and model complexity. What we have accomplished here is by building 177 6-node trees, we reached the overall likelihood performance of 0.585. And by the way, for those of you who have not seen it before, the likelihood, the smaller the cross entropy, the better the model performance. It's just something to keep in mind, because different performance measures will behave differently in terms of whether they need to be maximized or minimized. So the cross entropy needs to be minimized, and the smaller the value, the better the model performance. Okay, as I've said before, our difficulty at this stage is that we have a model of a large size and we want to find out whether it can be simplified or not. Now, one way to simplify the model is to start by re-examining what happens inside of the tree-net model and how it can be represented on some numeric scale. What I have done here, I moved back to that original toy example of saddle function, and I used our software to extract the very first tree from that sequence. It's a three-node tree. As you can see, it involves x1 and x2 jointly, and there is a simple set of rules that, depending on the values of x1 and x2, lead you to either terminal node 1, 2, or 3. At the bottom, you see the 3D rendering of that same tree structure, and that's what you saw on the very first heat map. Now, one way to think about this tree is if you have a data set where x1 and x2 are two available original predictors, then for each row in the data set, once you apply the tree, depending on what the values are, the record will land in terminal nodes 1, 2, or 3. Notice the bulk of records lands in terminal node 2. That red segment is 461. There's a smaller number in node 3 and even smaller number in node 1. Now, once the record falls into a terminal node, each terminal node is associated with the corresponding adjustment to the response surface, because in tree-net everything starts with a flat overall mean that fits everything, and then each tree introduces positive or negative adjustments to that picture. In this case, all of the adjustments are negative, but they are of different magnitude, and the whole point of this structure is to illustrate to an unprepared user that any tree in and of itself can be interpreted as a transformation of original predictors that produces a derived continuous variable, represented here with the symbolic name tree_1. Now, just like you could have introduced, say, a transformation, say something equals x1 squared, or you could have introduced a ratio of x1 over x2, or a log function of x1, or anything. From that point of view, a tree is no different because it essentially transforms original variables into a derived continuous variable. And now when you look at the tree-net sequence from this point of view, you will realize that the overall predicted response of a tree-net model with 187 trees is essentially a linear combination of 187 individual tree-based variables. And the next slide gives us a first glimpse into the essence of compression and the possible ways to improve and make this simplify the underlying tree-net model. We have just discovered that any tree-net model can be represented as the sum of tree-based variables, because each individual tree is just a transformation of the available set of inputs. Furthermore, the way the tree-net model is constructed, which is myopic and one thing at a time, this whole collection of trees is added in a one big linear combination with a coefficient 1.0 in front of each tree. So now the goal of model simplification and model compression could be simply restated as somehow figuring out a way to eliminate some of the trees, because we know trees are largely redundant. There's all that small learning overlap and all of the kind of redundancies that may happen in the original tree-net model. Now if we revisit all of the trees all together and somehow find a way which trees can be eliminated, and at the same time reweight joint contributions of all of the trees that are left, our hope is that the end result will at least be as accurate or nearly as accurate as the original model, and at the same time less complex because of all of the redundancy is being eliminated. And that's why we call it a post-processing technique. And this particular approach is known as ILE, Important Sample Learning Ensembles, and it accomplishes exactly that. So the only thing that remains to be answered here is to describe the underlying machinery that's used to make it possible. And that brings us to the next important topic of discussion, which is regularized regression methodology, which will provide the required and necessary machinery to accomplish the ILE task that we are looking for. Now, because we're talking about regularized regression, let me first show you a big picture of what's going on here and how everything can be laid out from these different points of view. The thing is that the literature on regularized regression is vast and complex. For a non-prepared user, it could be extremely intimidating. If you go out there and search for things like regularized regression, ridge, lasso, elastic net, anything of that nature, you will be overwhelmed with all sorts of math papers, stats papers, formula symbols, a lot of different stuff, and it's just plain intimidating, and unless you're really an expert in the field. So what I'm going to show here is that actually what's really going on is not that hard, and behind the fog of math you can see the real useful application that all of this boils down to. The GPS, Generalized Path Seeker, was introduced by Jerome Friedman roughly in 2008 in a series of papers, and is one of the very powerful evolutions of this whole machinery known as generalized regression. Now, in the conventional OLS regression, ordinary least squares, what happens is you have a learned sample and you have a collection of inputs, x1, x2, x3, etc. And the OLS regression builds a sequence of linear models. Let's say it can give you best one variable model, then the best two variable model, the best three variable model, etc. That's, by the way, is known as stepwise linear regression, or a variant of it. And the point is that each model gives you a final set of coefficients that optimizes performance on the learned sample. Now, if you read any book on OLS, usually all you ever see is the learned sample, and they completely ignore the way the concept of a test sample that's introduced in data mining is an attempt to validate or check the performance of your models and see whether they hold into the future. And there are reasons for that, etc., but I'll just stop at that. So the point is, OLS regression gives you a modeling solution that optimizes learned sample performance and completely ignores everything else. Now, people have shown in the past, though, is that if you take a standard OLS regression and modify coefficients a little bit, usually in the direction of shrinking those coefficients towards zero, what you may discover is that the performance of those models on an independent test sample may be better, even though you've sacrificed a part of the performance on the learned sample. And that's usually introduced as eliminating overfitting biases or learned biases and things like that. Now, generalized regression takes that concept and pushes it to the whole new level by constructing a large collection of a variety of different linear models, jointly called as path, and then later I'll introduce the concept of path. But in the bigger scheme of things, the large collection of models means that instead of having a one variable model as a given that optimizes performance on the learned sample, now we have a collection of models, all with one variables with varying coefficients. All of them are learned from the learned sample, but they kind of exist independently. Then you have a collection of two variable models, a lot of them with varying coefficients. They have a collection of three variable models, a lot of them with variable coefficients, and so on. And once you have that, we call it a pool of linear models, then you can employ at the very end a test sample to check the performance of each model and select the one that optimizes performance on the test sample. Now, if you're not happy with that additional partial kind of optimization on the test sample, you can always add a third sample here as a holdout or external validation or anything like that. And that's in a nutshell what this whole regularized regression literature is talking about. The core of the process, though, is how to construct all these individual collections of models. And that's why I have this next slide over here. And we call it path building process. And let's just look at it a little bit more details. We want to construct a collection of linear combination models. Everything starts at a so-called zero coefficient model, or people also call it intercept-only model, where all of the coefficients are zeros. None of the variables are included into the modeling step. So that's the starting point. Then, according to what's presented here, a variable selection strategy, the algorithm picks one variable out of the available candidates and starts changing the coefficient. So if you visualize the originally all variables have zero coefficients, then a variable is selected, and now the coefficient of that variable is being changed. So it goes from 0 towards certain value in sequence of steps, again, tightly controlled by what we call here a variable selection strategy. Now, once the variable has been exercised a certain number of steps, a second variable is added. And again, variable selection strategy keeps an eye on what happens in all the other variables, and at some point makes the decision to add the second variable in addition to the first variable. So now, instead of having just one coefficient, you have a set of two coefficients, and they will be jointly exercised in terms of either increments or decrements, again, according to the variable selection strategy. That will give you a sequence of two variable models. Then at some point, it will determine that another variable needs to be added, and once it's in, you will have a sequence of three variable models. The process can continue indefinitely, but usually it has some kind of user-imposed limit given by the largest number of variables that are allowed to enter into the model. And once all of the variables entered, the way the variable selection strategy works, all of their coefficients eventually converge to OLS solution. By the way, when I say OLS solution, I'm implicitly assuming linear regression or continuous target problem under least squares. There is the same identical machinery for logistic regression style GLM approach, and in SPM we have available both. One set for conventional regression and another set for logistic regression. But in any case, what we have accomplished here is that we've connected a model that has no coefficients and the model OLS solution of the finite user requested size with all of the intermediate solutions that include different modeling complexities in terms of the number of variables. The variable selection strategy happens to be the key here. Why? Because it controls when and how variables enter and how the coefficients are being jointly manipulated. The variable selection strategy itself, if you look at all of those fancy math papers, you'll see there is one parameter that specifically influences what happens and how the variable selection proceeds. That parameter is, in GPS is known as elasticity parameter. And by the way, the more generic name would be like shrinkage or amount of shrinkage or degree of regularization or amount of regularization. You'll find all different things out there. In GPS, it's elasticity, which is a real number, can be set to any values between 0 and 2, inclusive. Interestingly enough, three special cases emerge that show that GPS becomes a generalization, a fast approximation to other well-known variable selection techniques out there. For example, elasticity equals 2.0 turns out to be a fast approximation of ridge regression, meaning as step develops, you start with the zero coefficient model. Very quickly, you gobble up all of the available variables. Each step introduces one more variable. Once all of the variables have been gobbled up, their coefficients are very small at this point. Once they're all introduced, from that point on, the process develops jointly manipulating all of the coefficients, and then you have essentially a set of uniform shrinkage that is generally known as ridge regression, and that's one example of variable selection strategy. Another example comes from elasticity equals 1.0. It's a well-known, very interesting case, generally known as a lasso regression. Under lasso regression, variables are introduced in what could be called in a sparing manner. Again, you start with a zero coefficient model. One most kind of important variable, most promising variable is selected. The coefficient on that variable is exercised to a certain extent. Now, before the variable is fully introduced, which would have been essentially an OLS solution with one variable, so when that variable kind of downgraded just enough to become less important than the next best variable, a second variable is added. Now those two jointly exercised until they've become exercised enough such that someone else becomes equally important, and there are some modifications there and so on and so forth. That gives you the second way to a kind of important special case of variable selection strategy. And based on practical results, you'll see there's a good degree of compression, and those models tend to preserve accuracy very nicely. There is a third special case, elasticity of 0. It turns out it's a fast approximation of stepwise regression. What we do, we say, okay, start with a zero coefficient model, pick the variable that's most promising, introduce a sequence of models that essentially links zero coefficient model to OLS model with only one variable, which means you're basically squeezing out the full set, the complete magnitude of a signal available in variable 1. Once the variable being completely exploited, then the second variable enters. And that is a well-known approach as a stepwise forward linear regression, which itself is an approximation to best subsets linear regression. So according to that approach, eventually you get a collection of models that exercise the highest degree of compression, but at the same time you may want to keep an eye on the accuracy. And that's it. That's all we wanted, because now if I go back to the original slide, the Vitrinat model is a collection of trees with coefficients 1.0 all across the board, a lot of them redundant, collinear, all sorts of other things, strong, weak. Now we can treat those trees as individual variables, and we've seen how variables can be constructed based on the tree. And once you have those variables, you push them through GPS machinery. The GPS, according to whatever variable selection strategy, or in this case it becomes tree selection strategy that you used, the GPS will start exercising models of different size. Some trees will enter in the more aggressive earlier stages, others will never enter and will be eliminated. As long as everything is done in a nice way, our hope is that the end result will preserve the accuracy of the original model, and at the same time, by eliminating redundancies and other things, will give us a compressed version of TreeNet. Well, its time has come to see whether it works in real practice, so I'm going to switch back to the software. I'm picking the model here, and this time instead of TreeNet I go under Rule Learner Model Compression. It's a logistic binary. I'm still keeping the same settings of TreeNet, everything that we had before, except once I switch to this new analysis method, I have access to GPS control settings. And in here, I will use only compact, lasso, and ridge. the 3 elasticities that we introduced, even though you may experiment with any number of elasticities. It doesn't have to be 3, 4, 5. You could use 10, whatever the resources allow you to do. And so I'll use cross entropy as optimal selection. And under rule learner, at this point, we picked ISLE as the 3-net compression. So I click start. It proceeds by first generating a 3-net model, something that we've already done before. And then in the second step, it produces this post-processed GPS decomposition of the underlying 3 model, ISLE style. It takes about 15 seconds. The end result is shown here. I switch to cross entropy. And again, cross entropy, the smaller, the better, as the reminder. And a very nice thing has happened. The red curve shows test performance of 3-net. The red dotted curve, dashed curve, shows the performance of the ISLE post-processing. We know that the original 3-net had 177.3. What ISLE managed to accomplish here by revisiting those trees and reweighting them is that we reduced the number of trees down to only 84, and at the same time the overall performance improved, because the even original larger model has a cross entropy 0.585, and now it's down to 0.580. In fact, if you look at the curve itself, you have a nice universally improving envelope everywhere. So in this case, ISLE post-processing managed to preserve and even improve performance, and at the same time the best ISLE model here exhibits essentially 53% compression. Of course, this is just the suggested optimal. If you were interested in, say, reducing it even further, you could have gone here, for instance, 43 ISLE model, and at the same time performance is still essentially compatible with the performance of the original 3-net model. Now here's another thing that you can see here, and that is if you switch to some of these ISLE details and look at some of the additional displays, something that I don't have much time to talk about at this point. But if you look at the coefficients, here is what happens. Again, this column here shows 84 trees that were selected with that optimal cross entropy criterion, and the coefficients here represent essentially the coefficient in front of each tree. As you can see, not all of the trees were selected, some dropped out, and some of the coefficients are significantly greater than 1, which is basically showing that some trees took over the joint mutual contribution of all of the remaining trees that were dropped out. What's also instructive here is if you change some of these other displays, and it's a lot of fun to look at some of those displays and work with them on your own, as you move along the path solutions, and here we have 3 different variable selection strategy: compact, lasso, and ridge. As you move from the beginning of the path towards the end, you can see how different variable selection strategies gobble up variables. Again, let's look at it again. In the beginning, only one variable is introduced, and constant is irrelevant. But then, depending on what strategy you use, ridge wants to include more and more variables. Compact sticks to the existing variable, whereas lasso introduces variables in a more sparing way. As you progress it further and further, ridge eventually incorporates almost everyone. Compact wants to run whatever tree it's latched on, whereas lasso exercises more nice and versatile collections of coefficients. At some point you'll see that the compact forces a variable to be fully exploited. Ridge still does uniform shrinking, whereas lasso has all of those coefficients that highlight individual trees and exclude all of the remaining ones. This in and of itself, very fascinating thing, and I hope you may have a lot of fun studying those on your own. But I have to move on and introduce the next interesting comment here, which is, and again, I have a slide that highlights all of the compression and aisle, etc. But here's the next thing. Is this the only thing that we can do? Is this the best compression that we can accomplish? The answer is no. There is an even better way and more intriguing way to do something with the tree-net model. And we can arrive at it by revisiting the original tree decomposition into a variable. Again, it's the same slide as I had before, the very first tree in an exclusive OR problem. And notice that previously we would create just a single continuous variable that represents this tree. Now I can create a very different set of variables, a more detailed decomposition of this tree to the level of individual nodes. So each observation, we know, travels along the tree branches into a certain terminal node. Now I can introduce a binary variables that indicate whether the variable enters into terminal, the given record travels through internal node number 2. There's some records go through internal node number 2, some records don't. So I have 1, 0 combinations. I can also introduce another dummy variable, whether the record falls into terminal node 1, whether the record falls into terminal node 2, whether the record falls into terminal node 3. So therefore, having a 3-terminal node 3, I have introduced a 4 node-specific dummies that essentially, again, can be presented as yet another transformation of original inputs, this time producing a simple binary 0-1 node dummy. Now, once you accept that decomposition, at this point it becomes very clear that we can revisit our GPS approach and modify it such that in this case, instead of working at the tree level, it will work at the individual node level. So tree-net model in this case is decomposed into node dummies, both internal and terminal, from all of the individual trees. Of course, at this point, it's not as simple as each node enters with coefficient of 1.0 because you have to account for overlap and all the other things. But conceptually, it's irrelevant because all we need is those node dummies created as a collection of those variables. And once you have those node dummies, you can do GPS regression variable selection techniques and strategies to identify a subsets of nodes and the new sets of coefficients. And notice the node itself becomes the rule set because it's, say, in this case, in order to get into terminal node 1, you have to have a joint collection of rules. x1 has to be less than 1.47 and x2 less than negative 1.83. Once you run GPS, you can identify a subset of nodes. Let's see how it works in real life. Now, it's clear that all I need to do is to say, still use the rule learner, same set of inputs. This time, the only thing that will change is that under rule learner, instead of using I'll activate rule learner itself, which is extraction of rules from tree-net. Notice, because I use 6 node trees, potentially I'm creating 10 nodes for each tree, 4 internal nodes and 6 terminal nodes. The root node, of course, doesn't count because it's trivial. So I'm talking about processing 2,000 individual variables here. Needless to say, it's going to take somewhat longer because unlike I'll that worked with 177 tree-based variables, rule learner now works with about 2,000 individual node dummies. So as far as I know, it will take about 2 minutes. So while it's building that, I'm going to move on to the next slide and say a few final words on aisle compression. And this time it's a real life example, and there's some of our clients that used it in the web ad serving. So you have a web portal that leverages hundreds of 3-net models to optimize user experience. The problem that those guys faced is that their models could have, as we've said before, hundreds of thousands of trees, but because it was an online ad serving thing, they had a very strict requirement on the time that it can take to score individual models. So, and according to that requirement, whatever the internal configuration was, they could only afford scoring 30 individual trees. And then you have this unfortunate situation when you have a wonderful 3-net model that has 1,200 trees, but you can only use 30 trees in order to comply with your requirements. And therefore, what they've decided to do is that originally they would simply took the first 30 trees from the model and ignore everything else. By running, on the other hand, the aisle GPS-based post-processing, you can pick a very different set, a lot more informative set of 30 trees, therefore accomplishing compression and then sacrificing much smaller amount of predictive accuracy compared to that initial simple-minded kind of take the first 30 trees approach that they had before. Okay, hopefully the run is finished, so let me click back here, switch to cross entropy. And now you have a new rule learner run, this time, where again the red curve shows 3-net test performance, this time indexed by the total number of rules, not trees but rules. And then the aisle model shows, I mean not the aisle, the rule learner model has accomplished more than 91.5% compression, which is only 167 rules out of the initial set of 1982 coming from the original 3-net model. And look, as far as accuracy performance, this model is even better than aisle, because in aisle we had 0.580, this one is 0.575. So not only did we accomplish an even greater degree of compression by switching to rules, we also managed to improve performance on an independent test sample in this case. The performance-wise, depending on the application, it may or may not happen. There's sometimes it's hard to improve performance even further, but the nice thing about the rule learner, and it did happen in this case, the nice thing and the ultimate purpose of rule learner is that you can extract those rules and then also look at the details of those rules. And here's how it works. You click on the rules button. We have this entire collection of all of the individual rules extracted, all 167 of them, and as you can see, they come from different trees, different nodes, either terminal and sometimes internal when it determined that further splitting is not necessary. The mixture of all of the different trees, all of the different nodes, and we also have this point here, this support versus lift, a little graph that puts all of those rules as dots, and as you can see, some of these lifts goes above 2.0, meaning that in this case, in this specific problem, that means you found rules that lead into pure terminal nodes. In addition to that, is say if you're interested in studying more interesting rules, you can always switch to rules table here, sort everything according to test lift, and there you go, you have all the nodes and tree numbers and node numbers that correspond to the highest lift on the test sample and nicely presented in terms of support on the learn part and the test part of all of these individual partitions. And then you can go and analyze those individual rules, or you can simply notice tree number let's say this is a large support rule. Tree number 57, node number 7. So I go here, sort by trees. Tree number 57, node number 7. It's a terminal node. And this table here gives you the complete set of rules. You can cut and paste it, export it, do all of the other things. So that's the nice part about Rule Learner, is that not only do you compress your model one way or another, but you can also extract high informative rules. Now, the next little slide here, first I cut and paste, because we are recording this presentation, and this recording and the slides will be available after we finish. So if you're interested and want to revisit it again, that it can all be done, just let us know. But the next little example here shows a different application of Rule Learner, this time in banking. The data set dealt with loan defaults, which is a big issue, obviously, for bank analytics. The data set that I used had 16,000 accounts, which is basically 1/10 of the original data set. 43 predictors, overall default rate 10%, which means basically 10% of loans were defaulted. Now, by running Rule Learner, and so that you see these are not made up numbers, what I have here, I saved that model. It takes about 5-7 minutes to run, depending on how much resources you have. But I saved that model here so I can open it. And again, when you switch to all of these things, then you can find that this is the compression that happens to be in terms of Rule Learner. So it's not as high as an eBay data set, but it's still significant. And then when you go under rules, as we have seen, support versus lift, the nice thing about this example is that this time you have on the test sample a large number of rule sets producing the lift of 5 and 6. Now, in terms of default application, what it means is that even though 10% of loans defaulted in general, the Rule Learner identified rules where 50 or 60% of loans are defaulting. And then again, if you go on the rules table, very quickly you can identify which rule sets are there. And if I skip a few trivial ones, what you will see, all of those high lifts, 6.2, 6.1, 5.8, they are operating on supports that have hundreds of accounts. Because this data set is only a 10% sample of a much bigger data set, this essentially can be translated into thousands of accounts that can be quickly identified as having a greater than 50% chance of defaulting. And not only do you get the accounts, you also get all of the associated rules and actions that can be used presumably to address the issue at that specific banking application. So as you can see, the technology itself works. We've seen it working in a number of different practical applications: web advertising, online sales, banking, finance. We know some clients are trying to use it in environmental sciences. They're also in engineering. There's not enough time to cover all of those individual specific tasks, but this hopefully gives you enough information on what we managed to accomplish and where the technique can be used. The final slide, as the overall grand conclusion, is what is it that we have accomplished here? What is it that the technique allowed us to do? And also, in general, what is it that we are doing by going through all of these interesting post-processing operations? So when you think about model compression, the starting step is a tree building, And the tree building could be interpreted simply as a search engine for interesting transforms of the raw data. We saw individual trees are essentially an interesting transformation into a continuous variable. And individual trees are also interesting transformations into rule sets in the dummy nodes. Therefore, these transforms, by the way, are very nice because trees can handle all sorts of difficulties, missing data, outliers. They're also invariant to transformations of variables. They combine variables. They allow variables to interact. So when you have all of those transforms, you have access to the large number of all of the interesting things. The nice thing about it is that the transforms can also be discovered on very small samples of the data. Now, we know that the future is an analysis of big data. Now, based on everything that we've seen so far, you can generate a large set of individual transforms by operating on random samples from the big data as in a kind of very vast systematic way. So once you generate sufficient number of those transformations using either Hadoop clusters or using all sorts of kind of sampling techniques and distributed systems, once you have those transforms, the second stage, the generalized regression stage, which is essentially the GPS and all of the stuff that we talked about. The nice thing about GPS is that unlike individual trees, a GPS has a very simple implementation in terms of map reducing and distributed programming and model development. So you can use small samples to generate a collection of rules as large as you like, and then you can use distributed system to post-process that model to extract useful rule sets, useful trees, and therefore accomplish model compression on very big data sets. And that is the future. That is where we have a lot of development going on. The entire area is on the frontier of data mining, and it's kind of likely to become a very hot, big topic in the coming months and years as this technology advances to the new levels of understanding. This completes our presentation for today. I took a little bit more time. But hopefully you found it interesting, in some cases striking as something different, not traditionally encountered in data mining applications. I tried to short circuit all sorts of theoretical constructs. There was no formulas in here. The whole point was to illustrate practical applications of all of these technologies. The slides, the recordings will be available. If you have more questions, feel free to send those to us by email, online, and at some point, most likely next week, I will sit down and address as many of those questions as you send, and then everything should be fine from that point on. Now, I do see a few questions. What software did you use to show the decision boundaries for the exclusive OR problem with TreeNet? Okay, the exclusive OR problem, I used our own software. So I have this X1, X2 Grove right here. That's the TreeNet model. So then I show under display plots. I generated all of those plots, let's say for 195. I open this plot and then I switch it to this one. And you can use create plots, buttons, and live runs to generate all of those plots for any different number of trees. So that part is really nice. And as far as my laptop specifications, this is Intel Core i7. I have 8 gig of RAM. Running Windows 7. It's the machine is about almost 2 years old. So there's and I also have 4 cores. You can also see some of it shows 8 hyper-threadings, but technically it's 4 cores, and all of those parameters are there. Most of the stuff that I showed is already multi-threaded, so if you keep looking at the CPU usage as you build TreeNet models and or GPS models, the CPU usage goes up, and it leverages the power of multiple cores. Okay, there's more. Does compression alter relative variable importance in partial dependence plots of the underlying TreeNet model? Yes, it does, because you are fundamentally changing the actual layout of trees. And one part that is still incomplete is how to regenerate these partial dependence plots based on the new reduced post-process TreeNet model. So we're still working on that. Do you have a manual and rule learner or some tutorial? Well, this presentation is essentially the first step in that kind of tutorial. We're still working on manual. The software was just released less than a few weeks ago. It's still in the stages of final polishing, and the manual, as sad to say, in any development, that's the thing that comes last. So hopefully we'll be able to release the notes and the manual very quickly, because I know people, including our CEO Dan Steinberg, they're currently working on the final drafts of that. Yeah, that's basically all we have at this point. There will be more questions. You're welcome to write them to me and to other members of our teams. And by and large, that concludes then this webinar. This is Mikhail Golovny, Senior Scientist, broadcasting from Southern California. We had a cool rain yesterday, but it's beautiful and sunny outside. Everything is clear. And I hope all of you have the great rest of the day and a wonderful weekend. And I hope to see you soon at some point in the future, maybe even in person. Thank you, and have a great one.